This video is on power planning. In VLSI circuits, we are going to see how the power planning is performed in the core of your IC. See, what do you mean by power planning? In power planning, power grid network is created to distribute power to each part of the design equally. Let us say we are having an IC core in which, say this is your IC. In this IC, we need to distribute power to each and every cells in your ICs, is it? So that you need to plan it how to distribute this power. So that we can say it as a power planning. Okay, each and every part should be distributed. So it can be provided. Mainly it is used to provide power to macros and standard cells within the IR limit. See the current resistance limit, within the current resistance drop limit. So without dropping or with less drop, this power should be distributed. See, if you are placing the power distribution unit here, okay, and if you need to distribute the power to the corner of this cell, which means that there exists a lot of IR drop due to the large wires, okay, because of a large wire in the sense which is as the length of the wire is higher. Due to this, there exists an IR drop. So this has to be less during your distribution. And this can be done manually as well as automatically through the tool. In any way you can perform. In any of your power planning, there exist your inputs and outputs. If you consider your inputs, database with valid floor plan and power ring and power straps with spacing between VDD and VSS straps and power layer selection. These are to be considered during the inputs of your power planning. And during your outputs, design with power structure. Okay, how this power structure has to be designed, that needs to be considered during your power distribution. So that is what the output of your power. So let us say this is your power unit. The output of the power unit is, the design structure should be good. The design structure should be well mannered. Okay, and the database with valid floor plan needs to be considered for your inputs of your power plan, and power ring and power strap width. Okay, because if the width is too large, there exists an electromigration within your ICs or between your connections, and similarly the spacing between VDD and VSS. Let us say this is your VDD and VSS. How much spacing is to be provided between your VDD and VSS? That also consider as an inputs during your power planning. And power layer selection. So if you are designing in core layers, so that layer selection also need to be considered. So during this design, it can be done in 3 levels of power distribution. One is ring type, another one is strap, another one is rails. Okay, if you consider a ring, the carriers VDD and VSS is around the chip. See, if this is the chip area, if it is ring in the sense, it is to be connected around the ring. It is to be connected around the ring. Okay, and if it is straps, carries, sorry, if it is, okay, and carries VDD and VSS from this ring. From this ring, we need to carry the straps. Okay, and the rail is connect VDD and VSS to the standard cells of VDD and VSS. Okay, that is what your rails are mentioning. Okay, and this power planning management can be divided into 2 categories. One is core cell power management, another one is input output cell power management. If you consider the core cell power management, power rings are formed around your core. See, this is your IC. Okay, let us say this is your core and it should be planned around your cores. Okay, if any macro or IP is power critical, then create separate power ring for particular macro or IP. See, this is then if any macro or power is critical, if it is an important macro cell, that should be created separately. A power ring should be created separately for that macro. Let us say this is your IC core and this is your one of your macro within this IC, and this is your critical macro, which is an important macro. For this, the power ring should be created separately. So this is how you need to manage your core cell power. Okay, and the number of stabs are created based on power requirement. See, I am creating the stabs from this ring. Is it? It's sub-supply. We can say it is a sub-supply. This should be created based on the requirement. Okay, this is how it should be managed. And second category is input output cell power management. Input output cell power planning power rings are formed from input output cells, and trunks are created between core power rings and power pads. Okay, so this is what your input cell power management is. See, if there are any input output cells, from here it should be given to the core cells, and the trunks are created between your, see, if this is a core and this is your ring that is created for this is your ring that is created for your power distribution. So from this core power ring, the trunks are to be created between core power and power pads. Okay, the trunks needs to be created, which meant you can create the trunks that connects your power ring and your power pads. Okay, so now this is the figure show the complete power planning. See here, this is what we have discussed previously, that is given here. The trunks are created, these trunks are created between pads and your ring. See, these are the two rings that is formed. See, VDD and VSS are the two rings. Okay, see, these are the two rings, and these two rings are placed well enough so that the connection between these two should not be exist. Okay, if it exists, it's a short circuit, right? So it should not exist. And if there is any input and output, see, this is your input outputs. Okay, this is your input output pads, and this is also input output pads. Okay, the trunks need to be created between your rings and these pads. Okay, and similarly there should be a straps. See here that straps are used here, in which the powers are extracted either from VDD and VSS, is it, to give it to the standard cell core areas. Okay, and the rails are to be connected. Okay, the rails are to be connected from these rings. Okay, this is how a complete power planning is performed. And if you see, this figure shows the power ring around your macro. See, if there is any macro cell that needs a specific power, is it so, separate ring needs to be created for this. That is why a separate ring is created for this macro cell. Okay, the standard cell here is a basic cell that is used for your designing. So let us say you are designing a multiplexer. It utilizes, for example, it utilizes AND and OR gates, which means that the AND and OR gates are created in the standard core cell area. Okay, for that AND and OR gates, you need to give power supply. That has to be done in this way. Okay, and one more thing you need to consider during your power planning is IR drop analysis. The power supply in chip is distributed uniformly through metal layer across the design, and these metal layers have finite amount of resistance during your distribution of VDD and VSS. See here, we are connecting with the straps, is it? This VDD and this is VDD and this is for VSS, right? So this should be connected with limited value of IR drop. Okay, that is what a finite amount of resistance. When voltage is applied to this metal wires, current start flowing through the metal layer, and some voltage is dropped due to resistance of metal wire and current. This drop is called IR drop. This results in increased noise and poor performance, which means that if IR drop is increased, delay is increased. It's an important statement. If IR drop is increased, delay is increasing. Okay. Another such case is electron migration. One is IR drop, another disadvantage is electron migration. These two problems are to be considered during your power planning design. Okay. Electron migration is generally considered to be the result of momentum transfer from the electrons due to high current density. Let us say, see here, this is VDD and VSS. Okay. So I need to place this VSS very closer to the VDD. See, this shows a larger area, is it? But when you see in your design, this seems to be a very small minute area. Whenever high fluctuation is occurring, sometimes your VDD may enter into VSS. So that we can say it as an electron migration, a momentum transfer from the electrons due to high current density. Okay, see, this is one metal and this is another metal and this is dielectric, where due to the high current density, this metal will directly contact to this metal. through your dielectric. So that we can say it as an electron migration. The atom gets replaced from their original position, causing voids and hillocks in the metal layers. That is why the voids may occur and hillocks may occur in the metal layer. Heating may also accelerate electron migration because higher temperatures cause a higher number of metal ions to diffuse. Okay. The main techniques to solve this electron migration is increase the width of the wire. You can increase the width of your wire. The dielectric wire width can be increased, or buffer insertion can be done. Downsize the driver and switch the net to higher metal layer. Or if VDD and VSS got electron migration, that VDD and VSS can be given in an alternate strap layers. Okay, one is VDD. Let us say this is VSS. And next is VDD. If this metal strap is given through this, the electron migration can be reduced. So this is regarding your power planning and how the power planning can be performed and how it can be managed and what are the various things you need to consider during your power planning. That is what we discussed in this presentation.